Okay, hello everybody. So I've been introduced already, so let me just get to the meat of the talk. So I'm going to spend the next 20 minutes talking to you about the Apache Beam project, which was born out of Cloud Dataflow. And I'm really excited to be talking about that because I think it's a fascinating programming model for distributed data processing. So this is the rough outline of the talk. I'm going to approach Beam's programming model by showing you how Google arrived to this model from MapReduce until modern days. Then I'm going to talk a bit more in detail about the programming model, and then I'll talk about the current status of the Apache Beam project itself and how you can participate in it. So Google's data processing story. In the beginning, there was MapReduce. MapReduce paper was published in 2004, and this was a system that basically does one huge select query followed by one huge group by query. It was revolutionary in several ways. First, its main contribution is realizing that many data processing tasks can be formulated as a combination of these two kinds of queries, select and group by. The second contribution was building a really efficient and fault-tolerant system that takes care of everything except your functions that you apply in select and group by. It takes care of the fault tolerance and distribution and so on. So providing an abstraction on top of that. These were the two main contributions of MapReduce. And another one was actually that it provided this abstraction as a library rather than as a custom language such as SQL. And the reason for that was that there is already plenty of processing code written in different programming languages that would be harder to include as part of these queries. And another goal was to make it easy to run it programmatically from programs accomplishing higher level tasks. So these were the three main contributions of MapReduce. However, as I said, it was pretty low level, and people kept reinventing systems for sequencing a chain of MapReduces together. So approximately in 2010, a higher level tool was born called Flume Java. This was a tool for expressing higher-level data processing pipelines, basically directed acyclic graphs of data processing transformations. This is a graph with two types of nodes, collections and transforms. Collections logically contain data, not physically, and transforms take one or more collections and produce one or more collections as a result. So as a programmer, you construct the pipeline graph programmatically, and then you say, OK, please run this for me. And the system takes care of the rest, such as deciding how to best distribute the execution of this graph, how to optimize it, for example, avoid materializing some intermediate results, or do various database-like optimizations, like pushing down predicates, or avoiding grouping somewhere, or avoiding sorting, and so on. But the main contribution was really providing a high-level API. So this was a pretty successful project, and this is an example pipeline in the Flume Java API. It is remarkably similar to the modern Dataflow and Beam API, and it probably looks familiar to anybody who ever used Spark. So you manipulate these logical collections, and you apply transformations to them. This hypothetical pipeline reads some collection of sensor events from some kind of source, and parses them, and then computes, for example, the mean temperature by sensor location, and writes that to Bigtable. Relatively straightforward. So people used this programming model to process lots of data sets. Sometimes the data sets were pretty big, and sometimes the data sets were really, really big. And a recurring pattern in these kinds of big data sets is that keep growing over time, and they're usually organized by time. So these large amounts of data usually don't appear at once. They appear organically over time. So a very common pattern to process these kinds of data sets is, well, there's two common patterns. One is to have a periodically running batch job that processes the whole thing, which obviously at some point this stops scaling, because at some point the data set becomes too big to be processed quickly enough. And the other pattern is processing new chunks of this data as they arrive. This is probably more common. So this way of processing these kinds of large data sets has a couple of failure modes. So there is a couple of ways in which batch processing is not quite good. The first failure mode is latency. You cannot get low latency out of this kind of processing. So for example, if you have an hourly batch job, you're going to have at least 1 hour latency. So, that's something you cannot afford in many cases, such as fraud detection or anomaly detection or any kind of monitoring or rapidly learning machine learning models. So latency is a pretty big problem. And the second problem is sessions. By sessions, I mean when the data set can in some way be partitioned by user, which probably sounds familiar to many people in the room. And the actions of a particular user can be partitioned into sessions, which are like contiguous blocks of activity by this user with some gap between them. When you're processing data sets in these kinds of chunks, sessions get torn at chunk boundaries. Sometimes this is acceptable and sometimes it isn't. So the need arises to treat the data set as a continuous entity. So really, data sets like this are continuous and unbounded, and new data keeps arriving into them. And you have to embrace this fact. So upon embracing this fact, a bunch of people in the outside world came up with a number of stream processing systems, such as, well, you know, Storm and all kinds of others. And until recently, the state of the art was that stream processing systems did processing approximately. For example, they provided guarantees like events will be delivered at least once or at most once, or they might be duplicated sometimes or lost. So people believed that this was just something you have to deal with when processing streams. And in cases where exact results were remotely needed, people use something called the Lambda architecture, where you use a periodical batch job that computes exact results, and you have a stream system running in parallel that computes approximate refinements to these results. And at any point, you're kind of combining the results of these two systems. However, in the end, you always get an approximate results, and that's something that you cannot always afford to do. So at Google, we had systems where you cannot afford to have approximate results. You would think that it's not a big deal to lose or duplicate a single event because there's billions of these events, right? However, it becomes a big deal when you're talking about duplicating or losing rare events, such as detecting a fraud instance or detecting an outage from a stream of monitoring data or something like that. So if you have a system that inherently provides only at least once or at most once guarantees, you're going to have to deal with these problems for rare events too, and that's sometimes not acceptable. So in 2013, Google created a stream processing system called Millwheel. And this is a system that was designed to cope with these issues. Its main contributions were the following. First, it was deterministic, so it made no compromises on what kinds of events will be delivered and how many times. It works as if everything had been delivered exactly once, and it takes care of providing that abstraction. It turned out that this is possible. Another contribution Millwheel did was dealing with events in event time, which means that we're looking at the timestamps at which events happened rather than when they were ingested into the system, which can be sometimes wildly different. For example, if you're talking about some kind of in-game events in a mobile game that you're developing, if a user played the game in an airplane and then got back online and the game pushed these events to the server, then they're clearly delivered way behind when they happened. So Millwheel provided this kind of programming abstraction of directed acyclic graph of computations between which elements are flowing and provided an illusion of exactly once processing. However, it was relatively low level like MapReduce, so it did not really borrow the Flume Java API for high-level processing. So we ended up with two classes of systems. Streaming systems, though at least we figured out a way to get correct results, and batch systems, which were easy to program at a high level. And in the outside world, there was also a trade-off between correctness and latency. So about 2 years ago, we realized that these don't have to be different. And we need a programming model that allows us to program batch and streaming data processing not only similarly, but identically. In fact, many cases of batch processing are just poor imitations of stream processing because of some kind of need for a compromise is being felt by the people developing this, but the compromise does not have to be there. It is possible to have a system that is programmed identically in these modes. And this led to the development of a new programming model. And this was a huge chance to do things right in this space, because things have not been done before in this space, and we decided to do them right, and we summarized the principles of that programming model as what, where, when, and how. Let me talk about that in more detail. So the what part is the computation itself. So what kind of processing you're doing. For example, element-wise processing like filtering or transforming, cross-element processing like aggregations or groupings, and composite transforms that are basically just subgraphs of transforms that have a name so that you can reuse them multiple times or like do all kinds of other things on them. This is the easiest part. Now the more interesting part is the where. Like where in event time are you applying these transformations? When you're dealing with an unbounded data set, you cannot say that I want to compute the answer, because the data set is constantly changing, so there is no answer for the whole data set. So usually what you do is you slice the data set into some kind of chunks by time, and you emit answers for these chunks. So you say like the result for that particular hour is this. And there's different ways in which you can partition the data set into these chunks called windows. You can partition the whole data set into fixed or sliding windows, and many stream processing systems today allow this. But the programming model I'm talking about allows more flexible windowing. For example, it allows you to partition the data set by key and apply different windowing in different keys. This is necessary for session-based windowing. So this is an example of how windowing looks in a pipeline. It's just a transform. So yeah, it just fits into the programming model as a transform. For example, here we're windowing the data set into 2-minute windows. And then within every window, we're applying sums. The next more interesting part, when in processing time, in particular, when do we declare the results for a window complete? Or when do we emit the results for a window? Because of these data delays, new elements can arrive into the window. So it is possible that the result will change at any time. And you have to decide how are you going to emit the updated result. And there's another case for asking this when question. For example, if you're doing windows by day and you want to emit early intermediate results every hour. So that's also kind of a triggering condition for when to emit intermediate results. So the programming model of Apache Beam includes this concept called triggers, and they control when to emit intermediate results for windows. And there is an important related concept called the watermark. It is basically a guarantee provided by an input source on how late can the future data be. Unfortunately, I don't have enough time to talk about this in more detail, but I refer you to the similar excellent presentations by Francis Perry and Tyler Akido and other members of my team. So I'm going to continue talking about the fourth component, which is called how. How do the refinements relate? So what happens to the refinements to the results as late data arrives or as we emit intermediate results for a window? And there's different kind of strategies you can apply here, some more simple, some more complex. For example, you can just discard the new results, or you can replace old results with new results, or you can add them up together and subtract the old result to get kind of a running sum that should represent the total. So together, these four components allow us to deal with a wide variety of use cases, starting from classic batch processing, where we process the whole thing, all the way through windowing the data set and dealing with speculative results or late arriving data, and finally to expressing how late results affect old results and how they're communicated. So these are the pillars of this programming model. And they were implemented first in Google's project called Dataflow. Dataflow, my colleague Eric Anderson already talked about the Dataflow service in detail today, so I'm going to skip talking about it. I'll just mention that it's basically the programming model I'm talking about plus zero administration service, so you don't have to maintain any clusters or do any tuning. And the key topic of my talk is Apache Beam. So this January, the Dataflow team decided that it is prudent to make the project open source. So we decided to open source the programming model behind Dataflow and try to make it a unified programming model with different ways of running these pipelines. And the project was donated to Apache. And I'm excited to say that this Apache proposal was met with huge enthusiasm. It got, I think, 44 unanimous positive votes for being donated to Apache, and this is, as far as I know, the highest number of positive votes any Apache project has ever received. So this project is very much supported by the open source community, by many industry players. The committers include people from, well, Google, of course, but also PayPal, Tailend, Cask Data Artisans, and others. So what is Beam? First, it is an SDK. It is the API that allows you to construct and run pipelines. Currently, we have Java and Python APIs for constructing pipelines. And pipelines can be run in different ways. This is one of the key components of Beam, this portability across different runners. You can run it on your local machine, you can run it on Spark or on Flink, or you can run it on our service, which is, of course, hopefully more efficient. But if you cannot afford to run something on the cloud, you can run on Spark or Flink or locally. This is just an example pipeline written with the Beam API, but it looks pretty familiar to you by now, probably.
Is Scala available too, or just Java?
I believe Spotify has an open source project on GitHub providing a Scala SDK too. Yeah. So as I'm saying, it's an open source project and people are already actively participating. This is just a single slide view of the ecosystem. End users write pipelines. Pipelines use libraries of various transforms or data sources or sinks. These build upon language-specific SDKs available in different languages. These all implement the same Beam programming model, which I described before. And that programming model runs using a particular runner on a particular execution environment. So yeah, looks like I'm mostly out of time, but basically you can interact with the project at all of these levels. You can contribute new runners or write new transforms or write pipelines. So I invite you to do just that. And yeah, I think I'm going to finish here and ask, and I am ready to take questions.
So Spark provides a unified application, right? I think they have one caveat that streaming is micro. In this, I think we have done a good job with streaming to understand, like completely taking all possible permutations and combinations. But if you want to run any kind of machine learning or SQL, how would you do that right now? Or is there any plan for making Beam as a unified application as a combination of Spark?
So the Beam model is fully compatible with running machine learning computations in that. And I'm pretty sure that you would be able to do that using the Spark runner, which is optimized for low latency processing of batch data sets. I mean.
But the runner is going to be below Beam, right? But Beam doesn't provide the necessary API or.
So Beam is the programming model. It's how you express transformations, and machine learning algorithms are just examples of these transformations. So it's totally possible to write them yourself. Yes, please.
And of course, it is Apache incubating, right?
Yes, Beam is incubating. The first slide mentions that. Yes?
So you can run multiple, the runner will run multiple frameworks at the same time, like running continuous work jobs, continuous Flink jobs?
So the way this works is you write the pipeline and you say run this pipeline using this runner. So you can, for example, use the Spark runner to run this pipeline on Spark, or use the Dataflow Service runner to run it on the Dataflow Service.
Can I run both simultaneously?
Sure, it will be two separately running programs, but yes.
Relationship between Beam and Flink windowing API. Is Beam API higher level? Does it replace Flink windowing? What will happen there?
Mm-hmm. I believe the latest Flink windowing API was inspired by this programming model. In particular, they specifically added some windowing features to be able to implement this model and to implement the Flink runner. So I'm not familiar with more details of the Flink API, but I'm pretty sure that the windowing API is very similar because it was intended to be very similar. Yes.
So the temporal operators that are in Flink calling up into the Beam API as well?
I'm not that familiar with Flink itself.
Coincides before those types of operators?
I'm sorry?
Coincides before those kinds of operators?
I'm sorry, I'm not familiar with this. I'd love to learn more.
Thank you.
Yep. Thank you.
You too, guys.